we've been talking about trying to get the area under or between a curve and the x-axis, and we saw 3 approximation methods so far. Now the process of making those rectangles in general is going to lead us to what are called Riemann sums. And a Riemann sum is nothing more than using the technique or the approach that we used in getting areas using LRAM, RRAM, and MRAM, and applying it to a curve. But then what we're going to do is we're going to let the number of rectangles go to infinity. And when you do that, you'll see that that limit gives us the area, the actual true area between the curve and the x-axis. So to generalize the process, this is what I've done. I've taken just a generic function, f of x, and let's just say I'm interested in the area between the curve and the x-axis on the interval a to b. So what we're going to do is we're going to divide up that interval from a to b into n subintervals, and so I've marked it on the x-axis. So they're usually written with x's in subscripts, so x sub 0, x sub 1. You'll notice that x sub 0 is really just a, and x sub n is b. And what we want to do is we want to make them the same length. So the way you do that is you find the length of the subinterval. So that would be b minus a, and then you divide it up into the number of subintervals you want. That's n. So I'm going to call that my change in x. So I'm going to zoom in on that number line a little bit just so we can get a better picture here. So all I've done is I've taken, this is x naught, which is also known as a. This is x sub n, which is also known as b. And I'm just breaking this up into equal subintervals. So this would be x sub 1, this would be x sub 2, x sub 3, etc. The generic one would be x sub k, and then the one right before the x sub n one would be x sub n minus 1. And so now what we're going to do is so again, and they're all equal length, so this distance here, that's delta x, it's b minus a divided by n, as is this one here. Okay, so they're all the same length. The rectangles we're going to make have the same size base. So now what we're going to do, I'm going to put this up here in the corner. The next step is to choose some x value, because remember we need to determine the height of these rectangles. LRAM told us to go to the left endpoint and use that to determine the height. RRAM, we would go to the right endpoint. MRAM, we'd use the midpoint. You don't have to do anything in particular, and the process will still work. So this, what I'm writing is just to choose some x value on each interval. Okay, it doesn't need to be chosen in any particular way. So I'll just say it can be in any way. You could just randomly pick some. And I'm going to call the point you choose on the kth subinterval. We're going to call that c sub k. All right, so all we're doing in general is like on the first subinterval, you just pick some x value. It doesn't need to be in any particular way. I'm going to call that c sub 1. And then maybe over here in the second one, I'm going to pick a guy over here. I'm going to call that c sub 2. In general, just picking random x values. This guy here, c sub k. And then whatever I pick on the nth subinterval will be c sub n. So I've essentially kind of like put tags on the x-axis on each subinterval, And now what I'm going to do is I'm going to let that determine the height of my rectangle. So if we zoom in here, now I've got some, here's my C sub 1, here's my C sub 2, here's my C sub 3, here's my C sub k. These are what are determining the height of my rectangles. So I'd go up to the graph, and the y values determined by plugging in those c values on each subinterval, that determines the height of my rectangle. So I'm just going to kind of make these up a little bit. All right, so in general, we're making a bunch of rectangles in a particular way. All right, so just to recap, I'm saying, and this is just going to help for the notation of what we're going to write down. I'm going to say let f of c sub k, be the height of the rectangle on that interval. So that means that the total area is going to be the area of rectangle 1 plus the area of rectangle 2 all the way up to the area of rectangle n. But the area of rectangle 1 is the base, which we decided was changing delta x, b minus a over n, times the height, which would be f of c1. So it's f of c1 times the base plus f of c2 times the base all the way up to f of c sub n times the base. Now what we're going to do is we're going to write this in a different notation. So we're going to use sigma notation. So I'm adding up a bunch of guys here, and they all have the same structure: f of c sub something. So f of c. Now the somethings are changing. I'm going to put a little k there. F of c sub k times delta x, and k starts at 1 and goes up to n. So now here's the key move. We're going to let n, which represents the number of rectangles we made, go to infinity. So if we let n go to infinity, then we would be writing, so I'm just going to say that the sum of the n, I'm going to write that here too, s sub n, that's the sum of the areas of all n rectangles. S sub n would be the limit, as n goes to infinity, of this guy up here, and this notation, this is what we just defined here. I'm just going to squeeze this all up here. This notation is very it's really awkward, right? This limit here, we've come up with something actually really interesting, because that that limit is going to converge to the true area between the curve and the x-axis. And I'll show you a little animation that would make that clear. But this notation is really awkward. So instead of doing that, what the math community agreed on is to change this to be instead a big S for sum. So that's the integral sign. You're finding the area under the curve f of x with respect to x. So there's your dx. So the delta x becomes the infinitesimally thin rectangle whose width is dx. You can see the f of k gets replaced with f of x in general. And then you're getting the area in between the x values a and b. So we put an a and a b there. So this here is called the definite integral from a to b of f of x. Or that's what we would say. This is the definite integral from a to b of f of x dx. And the thing to note is that this gives us the exact area. This gives us the exact area under the curve of a continuous function. Or at least that's what the notation represents. Now I'm using the word under in quotations because we all know that under doesn't necessarily mean under. It's just, it means between the x-axis and the curve itself. But we're going to use under just to make it quicker to write down. Under the curve of a continuous function on the interval a to b. Alright, so that's the definite integral. That's what that notation means. So in the next few videos, the big thing is just to understand the notation. And at first what we're going to do is we're going to find areas geometrically. Then we're going to figure out some actually powerful ways to get areas under pretty much, or not any, but most functions that you've come across. And that's kind of the powerful tool, or the big powerful punchline to the second half of calculus. And you're going to see that it relates to what you've done so far. So for now, the definite integral has that notation, and in the next slide I'll show you a nice animation which shows how these rectangles converge to the true area.